encodes two variables. This is the sampling frequency, and y is a long vector. So let me just show you the first 10 entries of the vector. It's just 10 numbers, and you can just hear y if you want. It's music. If you want, you can just hear the first 1,000 samples, which is very short because the sampling frequency is 8,000, so this is 1/8 of a second. But let's say that we hear the first 2,000, 4,000, I guess is half a second. Okay, and then you can also plot y if you want. The signal, which is just an array of numbers, and you can zoom in here, and you can see these numbers. So it's a lot of numbers, and the discussion here is what's the meaning of the Fourier transform. So let me just focus on the first 10 samples, which is this. And now if I do, let's say, y short is y from 1 to 10, and now I can do FFT y short, and it responds back with 10 numbers. So the original 10 numbers of my signal are these, and this is the Fourier transform, the discrete Fourier transform of the signal. And the question here is, what's the meaning of these numbers? Now, the first thing to observe is that these are complex numbers, whereas my actual signal is real. And we're going to discuss a little bit what is the meaning of these. And the short answer is that these are dot products or projections of this vector, which is a 10-dimensional vector, onto some 10 special vectors, which are basically the harmonics, as we call them. So these are the dot products, which means the frequencies present into this vector. So to understand projections a little bit, let's start with two vectors. Let's say that I have a vector v0, and now I want to describe some arbitrary vector, let's say here x, which I'll just choose to be 2, 1. I would like to describe this vector as a linear combination of these two vectors. Example of this, let's say this is 1. And now I'm going to make a red color here, and this is the vector x. Now what I want to do is I want to write x as a number a0 times the vector v0 plus another number a1 times a vector v1. These two numbers here are giving me the amount of v0 that is contained in x and the amount of v1 that is contained in x. And I mean, in this little example, you can calculate them geometrically because you can project. So if you extend this line, you can project x onto v0, which means you're going to find this length here, like this, and you're going to find this length here. And you can see here that this length, if this length is around 1, this length is around half, and this length is more than 1 for sure, but less than 2 or something. So these are these numbers here that we're going to calculate explicitly right now. So the way we can calculate these numbers from geometry is basically using dot products. So the key thing we need is if I have two vectors, so this is, let's say that you have some arbitrary vectors x and y, and let's say that these are in 2 dimensions, so x has x1, x2, and y has y1, y2, then this is going to be a number, it's a scalar, so it's going to be the first coordinate of x times the first coordinate of y, plus the second coordinate of x times the second coordinate of y. Now, this is 2. Now, more generally, if you have vectors that have more than 2 coordinates, not in this example, but more generally, you will be adding all the coordinates together. So we are going to write x, y more generally. It's going to be the summation from I going from 1 up to the length, the dimension of the vectors, when you're going to take the ith coordinate of this guy and the ith coordinate of this guy, and you're going to add all of them together. Now the other thing that we're going to need in a second is that these vectors here have real coordinates, real values, but in a second they will also become complex. So then we need to take a complex conjugate here. A complex conjugate of a complex number, if the number is real, it's just the same number, but if a number is x plus jy, and you want to compute the complex conjugate of that number, it's going to be x minus jy. So it turns out that in order to compute the coefficient here, I need to divide, to normalize this, by the dot product of v0 with itself. So let's calculate this. The dot product of v0 with itself, v0 is this vector here, and the dot product with itself is 1 times 1 plus 1 times 1. So this is equal to 2. So this is going to be 1 over 2. Multiplied by the dot product of the vector x with v0. Okay, so x is 2, 1, and v0 is 1, 1. So the dot product of this vector is 2 times 1 plus 1 times 2. So it's equal to 3. Therefore, a0 is going to be 3 over 2. Similarly, you can calculate the other coefficient, which is going to be 1 over v1 dot product with itself times the projection of x onto v1. So this is 2 times 1 plus 1 times minus 1. So it's going to be 2 minus 1. And now just as a sanity check, let's see if this works. 3 over 2 times the vector 1, 1, which is indeed the vector x that we have here. So now we have shown that the vector x can be written as 3 over 2 times the vector 1, 1 plus 1 half times the vector 1 minus 1. Because there's a confusion between Matlab and the definition in the book, I'll just take a 1 over n, where n in our little example here is 2, because we're working with two-dimensional vectors. So I'll just take a 1 half outside, because Matlab likes to ignore that 1 half. 3 is a0 and 1 is a1. This is the first vector v0 and this is the second vector v1. And the whole point here is that a0 and a1 are the Fourier coefficients of the signal x. So a very quick way now, if I give you another vector, let's say y, and I tell you vector y is, let's say, 5, 3, and you want to calculate the discrete Fourier transform of this vector, you have to calculate these corresponding numbers here. And you can very quickly do that by taking the dot product of this vector with v0, which is the 1, 1 vector, and v1, which is 1 minus 1. So if you do that, you're going to find that the first Fourier coefficient of this is going to be the dot product of 5, 3 with 1, 1. And when you're taking this dot product, you're always basically adding the elements of the vector. So you're going to get 5 plus 3, which is equal to 8. And that's the first Fourier coefficient. And the second one is going to be the dot product of 5, 3 with a vector 1 minus 1. And that's going to be simply 5 times 1 minus 3 times 1. So it's the difference between the two coordinates. So it's going to be 2. Now, the meaning of these numbers is this is how much the frequency 1, 1, which is the 0 oscillations, how much this frequency is contained into your signal, 5, 3, or how similar your signal is with a constant signal. And this number here is telling you how similar your signal is with a signal that oscillates once, which means the 1 minus 1 signal. So, and the whole point here is that when n is equal to 2, so in 2 dimensions, you can either have the constant signal, which doesn't oscillate at all, or you can have the signal that oscillates 1. And basically, you're taking x dot product with this one, or you're taking x dot product with the one that oscillates only once. And these are your two Fourier coefficients. So now we're ready to find the Fourier transform of, let's say, the signal, 4-dimensional signal now. Which one? I'm going to do the 1, 2, 3, 4, 5. 1, 2, 3, 4. And this signal, if you do FFT, you are going to find 4 complex numbers that I'm going to call A0, A1, A2, A3. And now the key point is that this one is a dot product of this vector x with some basis vector, this Fourier basis vector that we call V0. And now the one thing we need to remember is that when I say a dot product between two vectors, that means take the first coordinate of the first vector and you multiply it by the first coordinate of the etc. And when these vectors have complex entries, then we put a complex conjugate here. And this is going to be a summation from 1 up to length 4 into our. So in order to calculate the Fourier coefficients, we have to find these basis vectors V0, and for the second Fourier coefficient, it's going to be the sum, the dot product of x with V1 and x with V2 and x with V3. Now the first one is pretty simple because the first vector is simply going to be what's called the constant frequency, or the constant vector 1, 1, 1, 1. And when you calculate the dot product of x with V0, you're going to get that A0 is going to be the first coordinate of x times the first coordinate of V0, so 1 times 1 plus 2 times 1 plus 3 times 1 plus 4 times 1, which is equal to 10. So this is what's called the zero frequency or the DC component, or how similar my signal x is to the constant frequency, or how much DC my signal contains. Now, in order to calculate the first Fourier coefficient A1, I basically need to calculate the vector V1. Okay. Now, what is V1? V1 is, I would like it to be a signal of 4 dimensions, 4 coefficients, which oscillates 1 time in 4 time slots. Now, before, when we had a 2-dimensional signal, we wanted something that oscillated once. So let me just do this here in 2 dimensions. In 2D, our V1 was simply the vector 1 minus 1, because this had a nice property that it oscillated exactly once in 2 time slots, because minus 1 has a nice property that minus 1 squared is equal to 1. Okay, great. But now I am looking for some number w, so that w to the 4th power is equal to 1. And of course, I can choose w to be 1, and that will work, or I can choose w to be minus 1, that will work. But these would not be oscillating once in 4 time slots. They would be higher harmonic. They would be oscillating 0 times, like the 1, or it would be oscillating once, like the minus 1. So they would be oscillating once every 2, so something that oscillates once every 2, of course, oscillates once every 4 also, but it's not the fundamental lower frequency. So I need what's called a primitive root, which means I need w to the 4th power to be 1, but I don't want w to the 2nd power to be 1. What's happening here to get that is I would like w to the 4 to be equal to 1, so that means that I would like w squared to be equal to minus 1, because then if I square this, I'm going to get exactly 1 raised to the 4th power. So the problem is that there is no real number that when squared gives you minus 1, so that's exactly why we go to imaginary numbers. So if I set w is equal to j, this works, because j to the 4th power is indeed minus 1 to the square, which is equal to 1. And the other thing to realize here is that there is no lower power that I can raise j and still get 1. So it is indeed the primitive 4th root of unity. So a picture here is very helpful. Now, if this is the complex plane, and this is the real axis, and this is the imaginary axis, this is 1, this is minus 1, this here is j, this here is minus j, and this is the unit circle, poorly drawn, unfortunately. Now what's happening is if you take 1, this is minus 1. Now if you take j, you start from here, take some red, you start from j. Now if you take j squared, you're going to get minus 1. So this is what's happening when you multiply j by itself. This is j squared. Then you multiply by j again. You are going to get minus 1 times j, which is equal to minus j. So this is j cubed. And when you multiply by j again, you are going to get to j4, j to the 4th power, which is equal to 1. Okay? So this is exactly this. The first one here is multiplying by j. So this is the W quantity that we need, and now we can define our signal V1, which is the signal that oscillates exactly once in 4 time slots, and it's going to be V1 is going to be the dot product of my signal X with this first harmonic oscillation V1. And the thing to remember here is that I'm taking a conjugate in the dot product. So this is going to be the dot product of the vector 1, 2, 3, 4. And this all adds up to be minus 2 plus 2j. So what this is telling you is that the amount of this harmonic, so this is the first frequency, a frequency that oscillated once in 4 time slots, and this is telling you how much of that frequency contained into this signal 1, 2, 3, 4, and you get a complex number from that. And if you want to quantify how much of this frequency is contained into my signal, you want to take the magnitude of A1. Okay, now we can calculate the second Fourier coefficient, which is A2, which is the projection of X into V2. So now I have to find the second signal. So what would be the second signal? So what I'm looking for now is a signal V2, is a signal that oscillates, that does, let's say, 2 cycles in 4 time slots. Okay, so how can I do that? Well, I can just get here, and I'm looking to find a complex number so that when I raise it to the 4th power, it has done 2 full circles. So if I just set W equals minus 1, it's going to work like that. In 1 time slot, it jumps here. In the 2nd time slot, it jumps back to 1. Again, in the 3rd time slot, it jumps here. And in the 4th time slot, it has jumped back to 1 again. So it has done exactly what I wanted it to do. In 4 time slots, it completed 2 full circles. So this is what I'm going to write here. I'm going to start from 1, minus 1, 1, minus 1. So this is the second oscillation, a faster frequency. And now I want to find how much does my signal contain this faster frequency. So I'm going to calculate the dot product of X with V2. And if you do that, it's going to be 1 times 1 minus 2 plus 3 minus 4. 1 minus 2 plus 3 minus 4. And you find that it is minus 2. So this is how much your signal contains the second harmonic, the signal that does 2 cycles in 4 time slots. That's great. So the next question is, what is V3? V3 is a signal that does 3 cycles in 4 time slots. In order to find a signal that in 4 time slots has done 3 full cycles, remember this here is minus j. So I would like to jump in each step 3/4 of a cycle. So this is basically how much I need to jump each step. So this is going to be minus j. So in the next time step, if I jump 3/4 of a cycle again, I am going to jump here. And this is going to be minus minus 1. And then again, if I jump 3/4 of a cycle from here, I am going to end up here, which is J. And then 3/4 of a cycle again. And I have looped back to 1. And observe that in 4 time slots, I completed 3 full cycles. So the vector v3 is going to start from 1, and then it's going to go to minus j, 1, minus j. The next thing to do is minus 1. The next thing to do is j. And the next thing to do is 1, so we have done a full cycle. Okay, actually we have done 3 full cycles, but another way of thinking about it is that I'm starting from 1 and I'm doing exactly what I was doing here, but I'm going backwards. So I start from 1, then I do a click backwards, so I'm in minus j, so I do another click backwards, and I'm in minus 1, and then I do another click backwards, and I'm in j, and then I do another click backwards, and then I am in 1 again. So 3 cycles in 4 time slots is the same as minus 1 cycle in 4 time slots. You sometimes see this in cars when their wheel is spinning very fast, and you see it in a camera, you may see the wheel turn slowly in the other side. So that's exactly what happened here. So now to calculate so minus j times 4. And this adds up to be minus 2 minus 2j, which is equal, by the way, to A1 conjugate, and this is a property of real valued signals. So these are the Fourier coefficients. So now, if we go in Matlab and we type x, here's the vector 1, 2, 3, 4, and I type ft of x, I'm finding the first Fourier coefficient is 10 plus 0j, so that's this 10, that's this 10 here. The second Fourier coefficient is minus 2 plus 2j, minus 2 plus 2j. The next one is minus 2 plus 0, which is minus 2. That's the next frequency. And the last frequency is minus 2 minus 2j, which is exactly this one.